In this module, you will learn about trigonometric functions. Take a look at the right-angled triangle ABC, right-angled at B. We know that in this triangle, the ratio of any two sides in a particular order gives rise to 6 different trigonometric ratios for the angle theta. That is, AB divided by AC is sin theta. BC divided by AC is cos theta. AB divided by BC is tan theta, and so on. Let's now extend the definition of trigonometric ratios to any angle in terms of its radian measure and study them as trigonometric functions. Consider a unit circle such that its center is at the origin. This circle intersects the x-axis at points A and C with the coordinates 1, 0 and -1, 0 respectively, and intersects the y-axis at points B and D with the coordinates 0, 1 and 0, -1 respectively. Let P be any point on the circle with the coordinates A, B in the first quadrant, such that angle AOP is equal to theta radians. We know that in a circle of radius r, if an arc of length L subtends an angle theta radians at the center, then L is equal to r theta. Using the formula, we get that length of arc AP is equal to theta. Drop a perpendicular from point P such that it intersects the x-axis at M. Point M is at a distance of A units from the origin on the x-axis and length MP is B units. Also, OP being the radius of the unit circle is equal to 1. Thus, we obtain a right-angled triangle OMP. By Pythagoras' theorem, the sum of the squares of the perpendicular and the base is equal to the square of the hypotenuse. Thus, A square plus B square is equal to 1. Now, corresponding to the angle theta radians, we define the trigonometric function cosine as cos theta is equal to A, and the trigonometric function sine as sin theta is equal to B. In equation 1, substituting the values of A and B, we get cos square theta plus sin square theta is equal to 1. This shows a relation between the sine and the cosine functions for any real theta, which is a very important result in trigonometry. Angles that are integral multiples of pi by 2 are called quadrantal angles. Let us find the values of sin theta and cos theta when theta is a quadrantal angle. When theta is equal to 0 degrees, point P coincides with point A. It implies that sin 0 degrees is equal to 0 and cos 0 degrees is equal to 1. When theta is equal to pi by 2, then point P coincides with point B. It implies that sin pi by 2 is equal to 1 and cos pi by 2 is equal to 0. When theta is equal to pi, point P coincides with point C. It implies that sin pi is equal to 0 and cos pi is equal to -1. And when theta is equal to 3 pi by 2, point P coincides with point D. it implies sin 3 pi by 2 is equal to -1 and cos 3 pi by 2 is equal to 0. This way, if we take one complete revolution from point P, we come back to the same point, P, again. It means that if we increase or decrease the value of theta by an integral multiple of 2 pi, the values of sin theta and cos theta do not change. Hence, sin 2n pi plus theta is equal to sin theta, where n is any integer. Also, as we saw, since sin 0 degrees and sin pi are 0, sin theta is equal to 0 when theta is an integral multiple of pi. That is, at 0, plus or minus pi, plus or minus 2 pi, and so on. Similarly, on increasing or decreasing the value of theta by an integral multiple of 2 pi, the value of cos theta also does not change. Therefore, cos 2n pi plus theta is equal to cos theta, where n is any integer. We just saw that the values of cos pi by 2 and cos 3 pi by 2 is equal to 0. Similarly, cos theta is equal to 0 when theta is an integral multiple of pi by 2. That is, at plus or minus pi by 2, plus or minus 3 pi by 2, and so on. Thus we can say that if sin theta is equal to 0, then theta is equal to n pi. And when cos theta is equal to 0, then theta is equal to 2n plus 1 into pi by 2, where n is any integer. Let us now define the other four trigonometric functions: tangent, cotangent, secant, and cosecant in terms of sine and cos. Tan theta is equal to sin theta divided by cos theta. Tan theta is defined when the denominator is non-zero. Now, cos theta is 0 when theta is equal to 2n plus 1 into pi by 2. Therefore, tan theta is defined for theta not equal to 2n plus 1 into pi by 2, where n is any integer. Cot theta is equal to cos theta divided by sin theta. It is defined when the denominator is non-zero. We know that sin theta is 0 when theta is equal to n pi. Therefore, cot theta is defined for theta not equal to n pi, where n is any integer. Secant theta is equal to 1 divided by cos theta. This function is defined when theta is not equal to 2n plus 1 into pi by 2, where n is any integer. Cosecant theta is equal to 1 divided by sin theta, which is defined when theta is not equal to n pi, where n is any integer. Using the above four trigonometric functions and the result sin square theta plus cos square theta is equal to 1, we can arrive at two more results that you have already studied in earlier classes. 1 plus tan square theta is equal to sec square theta, and 1 plus cot square theta is equal to cosec square theta. The table here shows the values of trigonometric functions for some standard angles. Let us now see the signs of trigonometric functions in different quadrants. Consider a unit circle such that its center is at the origin. This circle intersects the x-axis at points A and C, and the y-axis at points B and D as shown. Let P be any point on the circle with the coordinates A, B in the first quadrant, such that angle AOP is equal to theta radians. Let us now suppose a point Q in the fourth quadrant such that the measure of angle AOQ is also theta radians. However, this angle is negative as it is in the clockwise direction. It implies that the coordinates of point Q are A, minus B, since the y-coordinate in the fourth quadrant is negative. Now, corresponding to the angle theta radians, we define the trigonometric function cosine as cos theta is equal to A, and the trigonometric function sine as sine theta is equal to B. Let us find sine of minus theta. This is equal to minus B, since the y-coordinate of point Q represents sine of minus theta. This is equal to minus sine theta. Similarly, cos of minus theta is equal to A, since x-coordinate of point Q represents cos of minus theta, and this is equal to cos theta. Now, tan of minus theta is equal to sine of minus theta divided by cos of minus theta, and sine of minus theta is equal to minus sine theta, and cos of minus theta is equal to cos theta. Therefore, tan of minus theta is equal to minus tan theta. Similarly, cot of minus theta is equal to minus cot theta. Secant of minus theta is equal to secant theta. Cosecant of minus theta is equal to minus cosecant theta. Now, take any arbitrary point P with the coordinates A, B, which lies on the unit circle. The values of A and B lie between -1 and 1. In other words, the values of cos theta and sin theta lie between -1 and 1. Let us now see the signs of trigonometric functions in different quadrants. In the first and the second quadrants, y-coordinate is positive, which implies that the sine function is positive in the first two quadrants. In the third and the fourth quadrants, the y-coordinate is negative, and hence the sine function is negative. Similarly, x-coordinate of point P is negative in the second and the third quadrants, and therefore the cos function is negative in these quadrants. Similarly, x-coordinate is positive in the first and the fourth quadrants, and therefore the cos function is positive in these quadrants. Similarly, we can find the signs of the other four functions in different quadrants. From the above table, we can say that the sign of a trigonometric function depends upon the quadrant in which a point lies. On summarizing the table, we can say that in quadrant 1, all the trigonometric functions are positive. In quadrant 2, the sine and cosecant functions are positive. In quadrant 3, the tan and cot functions are positive. In quadrant 4, the cos and secant functions are positive. If we denote A for all, S for sine, T for tan, and C for cos, then the figure can be represented as shown. A trick to remember this would be to remember the phrase, all silver teacups, or a smart trick class, or add sugar to coffee, starting in the first quadrant. In this module, you will learn about angles and the units for their measurement. Consider two rays OA and OB originating from a point O. If one ray is fixed and the other is rotated about it, an angle is formed. An angle can be mathematically defined as the measure of rotation of a given ray about its initial point. Let ray OA be rotated in the anti-clockwise direction to meet ray OB. Ray OA is called the initial side of the angle, and the destination ray OB is called the terminal side of the angle. If the direction of rotation is counterclockwise, then the magnitude of the angle is conveniently taken as positive. Now, let ray OA be rotated in the clockwise direction to meet ray OB as shown. In this case, the magnitude of the angle is negative. The point of origin of the two rays of an angle is called the vertex. When the initial ray OA takes one complete revolution and comes back to its original position, then it makes an angle of 360 degrees. When rays OA and OB are in the opposite directions, an angle of 180 degrees is formed. The two units used most commonly for the measurement of an angle are degree measure and radian measure. First, let us discuss the degree measure. An angle is of measure 1 degree if the rotation from the initial side to the terminal side is 1/360th of a revolution. 1 degree is denoted as shown. A degree is divided into 60 equal parts, and each part is called a minute. That is, 1 degree is equal to 60 minutes. In other words, 1/60th of a degree is equal to 1 minute. A minute is further divided into 60 equal parts, and each part is called a second. That is, 1 minute is equal to 60 seconds, or 1/60th of a minute is equal to 1 second. Using this, 45 degrees and 15 minutes can be written as 45 1 divided by 4 degrees. These figures depict some angles in degree measure. In the first three figures, the direction of rotation being counterclockwise, the measure of the angle is positive. However, in the fourth figure, the direction of rotation is clockwise. Therefore, the measure of the angle is negative. In this case, the terminal side makes an angle of 45 degrees in the clockwise direction. Hence, this angle is of measure minus 45 degrees. Let's now discuss the radian measure. The angle subtended by an arc at the center of a circle whose length is equal to the radius of the circle is 1 radian. In other words, let theta be the angle subtended by an arc of a circle of radius r. If the length of the arc is also r, then theta is equal to 1 radian. If the radius of the circle and the length of the arc are equal to 1 unit, then theta is equal to 1 radian. Figure 1 here shows the measure of 1 radian, while figure 2 shows the measure of minus 1 radian. If the length of the arc of a unit circle is 2.5 units, then the angle made by the arc is 2.5 radians. Guess what is the angle subtended by an arc of length L? It is L divided by r radians. This is because in a circle of radius r, an arc of length r subtends an angle of 1 radian. And since equal arcs of a circle subtend equal angles at the center, an arc of length L subtends an angle of L divided by r radians. Hence, in a circle of radius r, if an arc of length L subtends an angle theta radian at the center, then L is equal to r theta. Let's now compare radian measure with degree measure. Consider a unit circle. We know that the circumference of a circle of radius 1 unit is 2 pi. We also know that an arc of length r of a unit circle subtends an angle of r radians at the center. Hence, 1 complete revolution of the initial side subtends an angle of 2 pi radians. Also, 1 complete revolution of the initial side is equal to 360 degrees. It implies that 360 degrees is equal to 2 pi radians, or 180 degrees is equal to pi radian. The table here shows the degree measures and radian measures of some standard angles. On substituting the value of pi as 22 divided by 7, 1 radian is equal to 57 degrees and 16 minutes approximately, and 1 degree is equal to 0.01746 radians approximately. So we can convert degree measure to radian measure or vice versa using the formulae shown. There is also an alternate formula to convert degree measure to radian measure or vice versa. If d represents the degrees and r represents the radians, then d divided by 90 is equal to r divided by pi upon 2. Let's take one example to convert degree measure into radian measure. Express 120 degrees in radian measure. We have d divided by 90 is equal to r divided by pi upon 2. Substituting the value of d and then simplifying, we get r is equal to 2 pi by 3. Alternatively, to convert degrees into radian measure, we multiply the degree by pi upon 180. Observe that in both the cases, we get 2 pi divided by 3 radian. Let's now convert 3 pi divided by 4 radian into degrees. In the formula, substituting the value of r and simplifying, we get d is equal to 135 degrees. Alternatively, to convert radian measure to degree measure, we substitute 180 in place of pi. On simplifying, we get 135 degrees again. An interval is said to be closed if both the endpoints are included in it. It is denoted by square bracket a comma b. If one of the endpoints is infinity or minus infinity, even then the interval is said to be a closed interval. An interval is said to be a half-closed or a half-open interval if only one of the endpoints is included. There are two types of half-open or half-closed intervals. If A is included, but not B, then the bracket is closed at A and open at B. It is denoted as shown. On the other hand, if A is excluded and B is included, then the bracket is open at A and closed at B. It is denoted as shown. An interval in which both the endpoints are excluded is called an open interval and is denoted as shown. Take a look at the table. The maximum value of sin theta and cos theta from 0 to 2 pi is 1. And the minimum value of sin theta and cos theta from 0 to 2 pi is minus 1. And if we increase or decrease the value of theta by an integral multiple of 2 pi, then the values of sin theta and cos theta do not change. This implies that the values of sin theta and cos theta lie between minus 1 and 1 for all theta belonging to R. In other words, the domain of sin theta and cos theta is the set of real numbers, and their range is the closed interval minus 1 to 1. Now, tan theta, which is equal to sin theta divided by cos theta, is defined when cos theta is non-zero. Now, cos theta is 0. When theta is equal to 2n plus 1 into pi by 2. Therefore, tan theta is defined for all theta belonging to the set of real numbers not equal to 2n plus 1 into pi by 2, where n is any integer. Or, tan theta is defined for all theta such that it is a real number and is not equal to 2n plus 1 into pi by 2, where n is any integer. This is the domain of tan theta. And the range is the set of real numbers R. Cot theta is equal to cos theta divided by sin theta. It is defined when sin theta is non-zero. Now, sin theta is 0 when theta is equal to n pi. Therefore, cot theta is defined for all theta belonging to the set of real numbers not equal to n pi, where n is any integer. This is the domain of cot theta, and the set of real numbers is the range of cot theta. Secant theta is equal to 1 divided by cos theta. This function is defined for all theta belonging to the set of real numbers not equal to 2n plus 1 into pi by 2, where n is any integer. This is the domain of secant theta. The value of secant theta does not lie between -1 and 1. Therefore, the range is the union of the closed interval -infinity minus 1 and the closed interval 1 to infinity. In other words, the range is the set of all real numbers y such that y is greater than or equal to 1 or less than or equal to -1. Cosecant theta is defined when theta is not equal to n pi, where n is any integer. Thus, the domain is the set of real numbers not equal to n pi, where n is any integer. And the range of cosecant theta is the same as secant theta. Let us now see the behavior of trigonometric functions in different quadrants. Take a look at the table again. The value of sin theta increases from 0 to 1, and the value of cos theta decreases from 1 to 0, when theta increases from 0 to pi by 2. From pi by 2 to pi, the values of sin theta and cos theta decrease from 1 to 0, and 0 to -1, respectively. When theta increases from pi to 3 pi by 2, sin theta decreases from 0 to -1, while cos theta increases from -1 to 0. And in the fourth quadrant, the values of sin theta and cos theta again increase from -1 to 0 and 0 to 1 respectively. Similarly, the behavior of the other four functions can be seen in different quadrants. Observe that the values of tan x and cot x repeat after an interval of pi. However, the values of sin x and cos x repeat after an interval of 2 pi. Hence, the values of cosec x and sec x will also repeat after an interval of 2 pi. Let us now draw the graphs of the trigonometric functions one by one, beginning with sin x. Let us take the values of x as 0, pi by 6, pi by 4, pi by 3, plus or minus pi by 2, plus or minus pi, and plus or minus 3 pi by 2. We know that sin x equal to 0 when x is equal to n pi, where n is any integer. Also, sin x is positive in the first and the second quadrants, and negative in the third and the fourth quadrants. Therefore, sin x is equal to 1 when x is equal to pi by 2 and minus 3 pi by 2. It is -1 when x is equal to minus pi by 2 and 3 pi by 2. Sin pi by 6 is half. Sin pi by 4 is 1 by root 2. And sin pi by 3 is root 3 by 2. Now, let us plot the values of x on the x-axis and the corresponding values of sin x on the y-axis. We get the graph as shown. From the graph, it is clear that the curve passes through the origin, and the minimum and maximum values of sin x are -1 and 1 respectively. It is also clear that the domain is the set of real numbers and the range is the closed interval -1, 1. Let's now move to the graph of cos x. Again, let us take the values of x as 0, pi by 6, pi by 4, pi by 3, plus or minus pi by 2, plus or minus pi, and plus or minus 3 pi by 2. We know that the value of cos x is 0 if x is equal to plus or minus pi by 2, plus or minus 3 pi by 2, and so on. Also, the value of cos x is -1 if x is equal to pi and minus pi, and 1 if x is equal to 2 pi minus 2 pi. Cos pi by 6 is root 3 by 2. Cos pi by 4 is 1 by root 2. And cos pi by 3 is 1 by 2. Now, let us plot the values of x on the x-axis and the corresponding values of cos x on the y-axis. We get the graph as shown. Observe that the graph of cos x does not pass through the origin, and the minimum and maximum values of cos x are -1 and 1, respectively. Proceeding on to the next function. Let us take the values of x as 0, pi by 6, pi by 4, pi by 3, plus or minus pi by 2, plus or minus pi, plus or minus 3 pi by 2. Then, the corresponding values of tan x are as shown. Plotting the values of x on the x-axis and tan x on the y-axis, we get this graph. Observe that the curve of tan x passes through the origin. Next, let us draw the graph of cot x. Like in the earlier functions, let us assume the same values of x. Then, the corresponding values of cot x are as shown. Plotting the ordered pairs x, cot x in the Cartesian plane, we get the graph of cot x. Next, let us draw the graph of secant x. Take the values of x as 0, pi by 6, pi by 4, pi by 3, plus or minus pi by 2, plus or minus pi, plus or minus 3 pi by 2, plus or minus 2 pi. The corresponding values of secant x are as shown. On plotting the values of x on the x-axis and the corresponding values of secant x on the y-axis, we get the graph of secant x. From the graph, it is clear that secant x does not lie between -1 and 1. Lastly, let us draw the graph of cosecant x. Take the values of x as 0, pi by 6, pi by 4, pi by 3, plus or minus pi by 2, plus or minus pi, plus or minus 3 pi by 2, plus or minus 2 pi. The corresponding values of cosecant x are as shown. On plotting the values of x on the x-axis and the corresponding values of cosecant x on the y-axis, we get the graph of cosecant x. Observe that the graph of cosecant x also does not lie between -1 and 1. In this module, you will learn about the trigonometric functions of sum and difference of two angles. Consider a unit circle such that its center is at the origin. Let A, B, C and D be points on the circle such that angle AOB is X, angle BOC is Y, and angle AOD is minus Y. As we already know, on a unit circle, the coordinates a, b of any arbitrary point P are given by cos x, sin x. Since the x-coordinate and the y-coordinate of an ordered pair represents the cosine and sine of the corresponding angles. Also, cos of minus x is cos x, and sine of minus x is equal to minus sine x. Therefore, point A has the coordinates 1, 0. B has the coordinates cos x, sin x. C has cos of x plus y, sine of x plus y. And D has cos of minus y, sine of minus y. Now, cos of minus y is cos y, and sine of minus y is equal to minus sine y. Therefore, D has the coordinates cos y, minus sine y. In triangles BOD and AOC, we have side OB is equal to side OC, and side OD is equal to side OA. Also, angle BOD is equal to y plus angle COD, which is equal to angle AOC. Therefore, by SAS congruence, triangle BOD is congruent to triangle AOC. This implies BD is equal to AC. That is, their squares are also equal. By distance formula, cos x minus cos y whole square plus sin x plus sin y whole square is equal to cos of x plus y minus 1 whole square plus sin of x plus y whole square. On simplifying, we get cos square x plus cos square y minus 2 cos x into cos y plus sin square x plus sin square y plus 2 sin x into sin y is equal to cos square of x plus y minus 2 cos of x plus y plus 1 plus sin square of x plus y. Since cos square theta plus sin square theta is equal to 1, we have minus 2 cos of x plus y is equal to minus 2 times cos x into cos y minus sin x into sin y. This implies cos of x plus y is equal to cos x into cos y minus sin x into sin y, which is a trigonometric function of the sum of two angles x and y. This is a very important result and is very useful in the derivation of other results. Now, let us prove that cos of x minus y is equal to cos x into cos y plus sin x into sin y. Replacing y by minus y in equation 1, we get cos of x plus of minus y is equal to cos x into cos of minus y minus sin x into sin of minus y. And since cos of minus x is cos x and sin of minus x is equal to minus sin x, cos of x minus y is equal to cos x into cos y plus sin x into sin y. Now, let's prove that cos of pi by 2 minus x is equal to sin x. Using result 2, cos of pi by 2 minus x is equal to cos pi by 2 into cos x plus sin pi by 2 into sin x. And simplifying, we get cos of pi by 2 minus x is equal to sin x. Next, sin of pi by 2 minus x is equal to cos x. Replace x by pi divided by 2 minus x in equation 3. We get the result. Now, let us prove one more important result. Sin of x plus y is equal to sin x into cos y plus cos x into sin y. Using equation 3, sin of x plus y can be written as cos of pi by 2 minus of x plus y. Rearranging the terms inside the bracket and using equation 2, we have cos of pi by 2 minus x into cos y plus sin of pi by 2 minus x into sin y. Now using equations 3 and 4, we get sin of x plus y is equal to sin x into cos y plus cos x into sin y. Now, let's prove sin of x minus y is equal to sin x into cos y minus cos x into sin y. Now, replacing y by minus y in equation 5. As cos of minus x is cos x and sin of minus x is equal to minus sin x, we get sin of x minus y is equal to sin x into cos y minus cos x into sin y. Let's now prove cos of pi by 2 plus x is equal to minus sin x. We know that cos of pi by 2 minus x is equal to sin x. Replacing x by minus x, we get cos of pi by 2 minus of minus x is equal to sin of minus x. This implies cos of pi by 2 plus x is equal to minus sin x. Let's now prove sin of pi by 2 plus x is equal to cos x. We know that sin of pi by 2 minus x is equal to cos x. Replacing x by minus x, we have sin of pi by 2 minus of minus x is equal to cos of minus x. This implies sin of pi by 2 plus x is equal to cos x. Similarly, we can prove that cos of pi minus x is equal to minus cos x. Sin of pi minus x is equal to sin x, and so on. Similar results for tan x, cot x, secant x, and cosecant x can be obtained from the results of sin x and cos x, which are shown in the table here. Let's now learn the tan and cot functions of the sum and differences of two angles. We know that cos theta is equal to 0, which implies that theta is equal to 2n plus 1 pi by 2, where n is any integer. Therefore, tan theta, which is equal to sin theta by cos theta, is defined only when theta is not an odd multiple of pi by 2. So let's now prove that tan of x plus y is equal to tan x plus tan y divided by 1 minus tan x into tan y. If x, y, and x plus y are not odd multiples of pi by 2. Beginning with the left-hand side, tan of x plus y can be written as sine of x plus y divided by cos of x plus y. Sine of x plus y is equal to sine x into cos y plus cos x into sine y, and cos of x plus y is equal to cos x into cos y minus sine x into sine y. On dividing the numerator and denominator by cos x cos y and simplifying, we get tan of x plus y is equal to tan x plus tan y divided by 1 minus tan x into tan y. Now, let us prove tan of x minus y is equal to tan x minus tan y divided by 1 plus tan x into tan y. Replacing y by minus y in equation, we get tan of x plus of minus y is equal to tan x plus tan of minus y divided by 1 minus tan x into tan of minus y. Since tan of minus y is equal to minus tan y, we get the required result. We know that sin theta is equal to 0, which implies theta is equal to n pi. Therefore, cot theta, which is equal to cos theta by sin theta, is defined only when theta is not a multiple of pi. Let's now prove that cot of x plus y is equal to cot x into cot y minus 1 divided by cot y plus cot x. If x comma y and x plus y are not multiples of pi. Cot of x plus y can be written as cos of x plus y divided by sin of x plus y. Now, cos of x plus y is equal to cos x into cos y minus sin x into sin y. And sin of x plus y is equal to sin x into cos y plus cos x into sin y. On dividing the numerator and the denominator by sin x into sin y and simplifying, we get cot of x plus y is equal to cot x into cot y minus 1 divided by cot y plus cot x. Now let us prove cot of x minus y is equal to cot x into cot y plus 1 divided by cot y minus cot x. Replacing y by minus y in equation, we get cot x plus of minus y is equal to cot x into cot of minus y minus 1 divided by cot of minus y plus cot x. Since cot of minus y is equal to minus cot y, we get the required result. In this module, you will learn about the trigonometric functions of sum and difference of two angles. Recall that sine of a plus b is equal to sine a into cos b plus cos a into sine b. Sine of a minus b is equal to sine a into cos b minus cos a into sine b. Cos of a plus b is equal to cos a into cos b minus sine a into sine b. Cos of a minus b is equal to cos a into cos b plus sine a into sine b. Tan of a plus b is equal to tan a plus tan b divided by 1 minus tan a into tan b. Tan of a minus b is equal to tan a minus tan b divided by 1 plus tan a into tan b. Let us derive some more formulae. First, let us prove that cos 2a is equal to cos square a minus sin square a which is equal to 2 cos square A minus 1, which is equal to 1 minus 2 sin square A, which again is equal to 1 minus tan square A upon 1 plus tan square A. We know that cos of A plus B is equal to cos A cos B minus sin A sin B. Replacing B by A in the formula, we get cos 2A is equal to cos square A minus sin square A. We know that sin square A plus cos square A is equal to 1, or sin square A is equal to 1 minus cos square A, or cos square A is equal to 1 minus sin square A. It implies that cos 2A, which is equal to cos square A minus sin square A, can be written as cos square A minus of 1 minus cos square A, or 2 cos square A minus 1. Now, substituting cos square A is equal to 1 minus sin square A, we get 1 minus 2 sin square A. Now, let us again consider cos 2A is equal to cos square A minus sin square A. Multiplying and dividing the right-hand side by cos square A, and then rearranging the terms, we get this. Now, this can be written as 1 minus tan square A divided by secant square A. Recollect that secant square A is equal to 1 plus tan square A. This implies cos 2A is equal to 1 minus tan square A by 1 plus tan square A. Let us now prove the result sin 2A is equal to 2 sin A into cos A, which is equal to 2 tan A divided by 1 plus tan square A. Recall that sin of A plus B is equal to sin A into cos B plus cos A into sin B. Replacing B by A, we get sin 2A is equal to 2 sin A into cos A. Now multiplying and dividing by cos A, we get 2 sin A by cos A into cos square A, which is equal to 2 tan A divided by secant square A. It implies that sin 2A is equal to 2 tan A divided by 1 plus tan square A. Now, let us find the formula for tan 2A. Recall that tan of A plus B is equal to tan A plus tan B divided by 1 minus tan A into tan B. Replacing B by A in the formula, we get tan 2A is equal to 2 tan A divided by 1 minus tan square A. Now, let us learn some formulae that involve an angle 3A. The first is sin 3A is equal to 3 sin A minus 4 sin cube A. Consider the left-hand side. Sin 3A can be written as sin of 2A plus A. Recall that sin of A plus B is equal to sin A into cos B plus cos A into sin B. So, sin of 2A plus A can be written as sin 2A into cos A plus cos 2A into sin A. Now, sin 2A is equal to 2 sin A cos A, and cos 2A is equal to 1 minus 2 sin square A. On substituting, we get 2 sin A into cos square A plus 1 minus 2 sin square A into sin A. Substituting cos square A is equal to 1 minus sin square A. We get 2 sin A minus 2 sin cube A plus sin A minus 2 sin cube A. On simplifying, we get sin 3A is equal to 3 sin A minus 4 sin cube A. Let us now prove that cos 3A is equal to 4 cos cube A minus 3 cos A. Cos 3A can be written as cos of 2A plus A. Recall that cos of A plus B is equal to cos A into cos B minus sin A into sin B. Using this, cos of 2A plus A can be written as cos 2A into cos A minus sin 2A into sin A. We know that cos 2A is equal to 2 cos square A minus 1, and sin 2A is equal to 2 sin A into cos A. On substituting the values and simplifying, we get cos 3A is equal to 4 cos cube A minus 3 cos A. Now, let us prove tan 3A is equal to 3 tan A minus tan cube A divided by 1 minus 3 tan square A. Tan 3A can be written as tan of 2A plus A. Recall that tan of A plus B is equal to tan A plus tan B divided by 1 minus tan A into tan B. Using this, tan of 2A plus A can be written as tan 2A plus tan A divided by 1 minus tan 2A into tan A. Substituting tan 2A is equal to 2 tan A divided by 1 minus tan square A, we get this. On simplifying, we get tan 3A is equal to 3 tan A minus tan cube A divided by 1 minus 3 tan square A. Let us now prove some more results. The first one is sin of A plus B plus sin of A minus B is equal to 2 sin A into cos B. Consider the left-hand side. Sin of A plus B is equal to sin A into cos B plus cos A into sin B, and sin of A minus B is equal to sin A into cos B minus cos A into sin B. On simplifying, we get 2 sin A cos B. Hence the result. The second is sin of A plus B minus sin of A minus B is equal to 2 cos A into sin B. Consider the left-hand side. Again, sin of A plus B is equal to sin A into cos B plus cos A into sin B, and sin of A minus B is equal to sin A into cos B minus cos A into sin B. On simplifying, we get 2 cos A sin B. Hence the result. The third is cos of A plus B plus cos of A minus B is equal to 2 cos A into cos B. Consider the left-hand side. Cos of A plus B is equal to cos A into cos B minus sin A into sin B. And cos of A minus B is equal to cos A into cos B plus sin A into sin B. On simplifying, we get 2 cos A cos B. Hence the result. The fourth one is cos of A plus B minus cos of A minus B is equal to minus 2 sin A into sin B. Consider the left-hand side. Again, cos of A plus B is equal to cos A into cos B minus sin A into sin B, and cos of A minus B is equal to cos A into cos B plus sin A into sin B. On simplifying, we get minus 2 sin A into sin B. Hence the result. Let us now prove few more formulae. Let us assume that A plus B is equal to C and A minus B is equal to D. On solving for A and B, we get A is equal to C plus D by 2 and B is equal to C minus D by 2. Now, substituting these values in the identities, we get next, let us prove sin of A plus B into sin of A minus B is equal to sin square A minus sin square B, which is equal to cos square B minus cos square A. Consider sin of A plus B into sin of A minus B. Substituting sin of A plus B is equal to sin A into cos B plus cos A into sin B, and sin of A minus B is equal to sin A into cos B minus cos A into sin B. On simplifying, we get sin square A into cos square B minus cos square A into sin square B. This is further equal to sin square A into 1 minus sin square B minus 1 minus sin square A into sin square B. On simplifying, we get sin square A minus sin square B. Now, sin square A minus sin square B is equal to 1 minus cos square A minus of 1 minus cos square B. This is equal to cos square B minus cos square A. Now, let us prove cos of A plus B into cos of A minus B is equal to cos square A minus sin square B, which is equal to cos square B minus sin square A. Consider cos of A plus B into cos of A minus B. Cos of A plus B is equal to cos A into cos B minus sin A into sin B, and cos of A minus B is equal to cos A into cos B plus sin A into sin B. On simplifying, we get cos square A into cos square B minus sin square A into sin square B. This is further equal to cos square A into 1 minus sin square B minus 1 minus cos square A into sin square B. On simplifying, we get cos square A minus sin square B. Now, cos square A minus sin square B is equal to 1 minus sin square A minus of 1 minus cos square B. This is equal to cos square B minus sin square A. Now let us prove the last result. Using the formula tan of A plus B is equal to tan A plus tan B divided by 1 minus tan A into tan B. Tan pi by 4 plus A is equal to tan pi by 4 plus tan A divided by 1 minus tan pi by 4 into tan A. This is equal to 1 plus tan A divided by 1 minus tan A, as tan pi by 4 is equal to 1. Now, substituting tan A is equal to sin A by cos A, we get cos A plus sin A divided by cos A minus sin A. Let us take one more example. Find the principal solutions of sin x is equal to half. We know that sin pi by 6 is equal to half. Also, the sine function is positive in the second quadrant. So when x is equal to pi minus pi by 6 or 5 pi by 6, the value of sin x is equal to half. Hence, pi by 6 and 5 pi by 6 are the principal solutions of sin x is equal to half. We know that trigonometric functions are periodic functions. The functions sine, cos, cosecant and secant repeat after an interval of 2 pi, while the functions tan and cot repeat after an interval of pi. This implies that we can generalize the solutions of trigonometric equations with the help of the periodicity of trigonometric functions. For example, sin theta is equal to 0 implies that theta is equal to n pi, which gives all the solutions of the trigonometric function sin theta is equal to 0. When the solution set of a trigonometric equation is an expression involving an integer n, such a type of solution is called the general solution of the trigonometric equation. In this case, theta is equal to n pi is the general solution of the trigonometric function sin theta is equal to 0. Similarly, cos theta equal to 0 implies that theta is equal to 2n plus 1 pi by 2, which gives all the solutions of the trigonometric function cos theta is equal to 0. In this case, theta is equal to 2n plus 1 pi by 2 is the general solution of the trigonometric function cos theta is equal to 0. Let's now prove some theorems that will help to find the general solutions of trigonometric equations. The first theorem is, for any real numbers x and y, sin x is equal to sin y implies that x is equal to n pi plus minus 1 whole raised to the power n into y, where n belongs to the set of integers. Let's begin with the proof. For any real numbers x and y, we have sin x is equal to sin y. This implies sin x minus sin y is equal to 0. Now, sin x minus sin y is equal to 2 cos of x plus y by 2 into sin of x minus y by 2. That is, the product of cos of x plus y by 2 and sin of x minus y by 2 is 0. This implies either cos of x plus y by 2 is equal to 0 or sin of x minus y by 2 is equal to 0. We know that if sin theta is equal to 0, then theta is equal to n pi, and if cos theta is equal to 0, then theta is equal to 2n plus 1 pi by 2, where n is any integer. Therefore, x plus y by 2 is equal to 2n plus 1 pi by 2, or x minus y by 2 is equal to n pi, where n is any integer. Or x is equal to 2n plus 1 into pi minus y, or x is equal to 2n pi plus y, where n is any integer. We know that minus 1 raised to the power of 2n plus 1 is equal to minus 1, and minus 1 raised to the power of 2n is equal to 1. Therefore, x can be written as 2n plus 1 into pi plus minus 1 whole raised to the power of 2n plus 1 into y, or x is equal to 2n pi plus minus 1 whole raised to the power of 2n into y, where n belongs to the set of integers. Now, 2n plus 1 constitutes all the odd numbers, and 2n all the even numbers, and all the odd numbers and even numbers taken together make the set of integers. Hence, on combining the two results, we get x is equal to n pi plus minus 1 whole raised to the power of n into y, hence the result. Let's now move on to the next theorem. For any real numbers x and y, cos x equal to cos y implies that x is equal to 2n pi plus or minus y, where n belongs to the set of integers. Let's begin with the proof. For any real numbers x and y, we have cos x is equal to cos y. This implies cos x minus cos y is equal to 0. Cos x minus cos y is equal to minus 2 sine of x plus y by 2 into sine of x minus y by 2 is equal to 0. That is, the product of sine of x plus y by 2 and sine of x minus y by 2 is 0. This implies either sine of x plus y by 2 is equal to 0, or sine of x minus y by 2 is 0. We know that if sine theta is equal to 0, then theta is equal to n pi, where n is any integer. Therefore, x plus y by 2 or x minus y by 2 is equal to n pi, where n is any integer. Or x is equal to 2n pi minus y, or x is equal to 2n pi plus y, where n is any integer. On combining, we get x is equal to 2n pi plus or minus y, where n is any integer, hence the result. Let's prove the last theorem. If x and y are not odd multiples of pi by 2, then tan x is equal to tan y implies x is equal to n pi plus y, where n belongs to the set of integers. Let's begin with the proof. Suppose x and y are not odd multiples of pi by 2 and tan x is equal to tan y. This implies tan x minus tan y is equal to 0. Or sin x upon cos x minus sin y upon cos y is equal to 0. Or sin x into cos y minus cos x into sin y upon cos x into cos y is equal to 0. Now, sin x into cos y minus cos x into sin y is equal to sin of x minus y. So we have sin of x minus y upon cos x into cos y is equal to 0. This implies sin of x minus y is equal to 0. We know that if sin theta is equal to 0, then theta is equal to n pi, where n is any integer. Thus we can say that if sin of x minus y is equal to 0, then x minus y is equal to n pi, or x is equal to n pi plus y, where n is any integer. Hence the result. Let's now find the solution set of sin x equal to minus 1 upon root 2. Let's begin with the solution. Given sin x is equal to minus 1 upon root 2. Now, sin pi by 4 is 1 upon root 2. Therefore, sin x is equal to minus sin pi by 4. This further implies that sin x is equal to sin of minus pi by 4, since sin of minus theta is equal to minus sin theta. This implies x is equal to minus pi by 4. Let alpha be the principal solution of sin x is equal to minus 1 upon root 2. Then alpha is equal to x is equal to minus pi by 4. Recall that for any real numbers x and y, sin x is equal to sin y implies x is equal to n pi plus minus 1, whole raised to the power n into y, where n belongs to the set of integers. The solution set is equal to n pi plus minus 1 whole raised to the power of n into minus pi by 4, where n is any integer, or n pi plus minus 1 whole raised to the power of n plus 1 into pi by 4, where n is any integer.